next we're going to look at some properties of sequences, and the first one is the squeeze theorem for sequences. So you may recall the squeeze theorem for functions and their limits was back in chapter 1 of Cal 1, and the idea was that if you had two functions that were formed a boundary on either side of a third function, and those two functions happen to have the same limit, then that would mean the third function would also have to have the same limit. It was like it was being squeezed between the two functions at that point. And this is the same kind of idea, it's just we're talking about two sequences converging on the same point, and then you've got your third sequence in the middle. So it's the same kind of idea. Beyond a certain point, it's always between a sub n and b sub n, so that means that it would have to have the same limit as well. So with this example, we've got negative 1 to the nth power times 1 over n factorial. And if you let that be your c sub n, and if you let your a sub n be negative 1 over 2 to the nth power, and you let your b sub n be 1 over 2 to the nth power, then you can show pretty easily that c sub n is between those two. And the way that you would verify that, obviously, you're going to have the negative, positive on either side of that. But if you think about 1 over 1 factorial, that's 1 over 1. That's going to be less than or equal to 2 factorial. But what ends up happening, 1 over 2 factorial, what ends up happening is beyond a certain point, you end up with, once you get to n to the 4th power, n equal 4, you get the following. So when n is equal to 4, it switches from being 1 over n factorial being greater than 1 over 2 to the nth power to 1 over 4 factorial being less than 1 over 2 to the 4th power. And then the negative side of that means that that this would be on the other side. So for all n greater than or equal to 4, this is the case. So since the limit as n approaches infinity of 1 over 2 to the n, or b sub n, is equal to 0, and the limit as n approaches infinity of negative 1 over 2 to the n also equals 0, by the squeeze theorem, we would say that the limit as n approaches infinity of negative 1 to the nth power times 1 over n factorial is also equal to 0. Another way you could find the limit of this function that we were just looking, or sorry, a sequence that we were just looking at, is using the absolute value theorem. And this says for the sequence, the a sub n, if the limit as n approaches infinity of the absolute value of a sub n equals 0, then the limit as n approaches infinity of a sub n equals 0. So again, we've got c sub n equals negative 1 to the nth power over n factorial. So the limit as n approaches infinity of the absolute value of that, all that's really going to change is we're no longer going to have this oscillating negative 1. So that's the same thing as the limit as n approaches infinity of 1 over n factorial. And if you've got a fixed number over something that is growing infinitely large and a factorial grows very, very quickly, you know that this is going to be 0. So that means that by theorem 9.4, that also means that the limit as n approaches infinity of our original c sub n is equal to 0, so it converges to 0. So you can use that in that situation as well. One thing that can be really handy when dealing with sequences is being able to recognize patterns of sequences and come up with that a sub n formula for the nth term. And I'm just going to be honest with you, some people take to this right away and it just makes total sense. Some people it takes a little practice and it's not super intuitive. So it just kind of depends on whether you're comfortable with it or not, but you can get there eventually. So this says find a sequence a sub n whose first 5 terms are 1, 1/2, 1 over 6, 1 over 24, and 1 over 120. And I see right now, because I've dealt with factorials enough, I recognize that I could write this term as 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, and 1 over 5 factorial, because 5 factorial is 120, 4 factorial is 24, and so on and so forth. So for this one, I would call a sub n 1 over n factorial. Now, the cool thing about this is there's usually more than one way to think about it. So another thing that you could say is you could say a sub n is equal to 1 over n times a sub n minus 1. Now let's think about this, because I've got basically the previous term times 1 over n. So if the previous term here was 1 over 4 factorial and I multiplied that by 5, I would get, in the denominator, I would get 1 over 5 factorial. And this one, of course, comes with the caveat that you need a base case, a sub 1 equals 1. So both of these are valid. This one is a non-recursive or a closed formula, and this is a recursive formula. It just depends on what your needs are. So either one of those would be perfectly valid. Okay, this says find a sequence a sub n whose first 4 terms are 2, 8, 14, and 20. So again, you could do a recursive version of this if you want. I look at what happens from one to the next, and I notice that between each term I'm adding 6. So I could say a sub n is equal to a sub n minus 1 plus 6, and we'll call a sub 1 2. So 2 plus 6 is 8, 8 plus 6 is 14, so on and so forth. Non-recursively, if I don't want a recursive formula for some reason, I could just say a sub n is equal to, let's see, if we want n to be 1, I could do 6 times 1 minus 4, see if that works. 6n minus 4, so this would be 12 minus 4, this would be 6 times 3 would be 18 minus 4, and then, yeah, 6 times 4, yeah, so 6 times 4 minus 3 would be 24 minus 4. So this would work as well, and you wouldn't need a base case. For this one, we have 1 over 2 times 3, 2 over 3 times 4, 3 over 4 times 5, 4 over 5 times 6. You could do this with factorials, or you could just let a sub n, and sometimes I use the curly braces, sometimes I don't. It just kind of depends on context. But I'm going to let n equal 1 here, so this will be n over, how about n plus 1 times n plus 2? So that would be 1, 2, 3, 2, 3, 4, 3, 4, 5. Yeah, that works. So again, with these, sometimes you just have to practice. Sometimes you just have to try things, and you may try something and it doesn't work, and then you can just kind of go back and look at it and say, okay, what other patterns do I possibly see here? Look at what happens from one term to the next, and look for groupings like what we saw here. And it also helps to be familiar with, like we said a minute ago, the values of the different maybe powers of 2, powers of 3, or the values of the different factorials. Finally, in this video, we have a definition of what we call monotonic sequences. A sequence a sub n is monotonic when its terms are non-decreasing or when its terms are non-increasing. So it's basically not switching back and forth from increasing to decreasing. It's either always going down or staying the same, or always going up or staying the same. And with that, we have a bounded sequence. A sequence a sub n is bounded above when there's a real number m such that a sub n is less than or equal to m for all n, and this is called an upper bound. A sequence a sub n is bounded below when there is a real number n such that n is less than or equal to a sub n for all n, and that number is called a lower bound of the sequence. And if it's bounded above or below, we call it just bounded. Now, a couple of things to point out here. Notice that it doesn't say the upper bound, it says an upper bound or a lower bound. So you can name an upper bound of the sequence and say that it's bounded without being super precise about just how bounded it is. And there's topics that you can go into about finding the least upper bound or the greatest lower bound and different things like that, but we're not really concerned about that at this point, just whether or not it's bounded at all. And if a sequence happens to be bounded and monotonic, then it converges. So that's a route you can take as well if you're not sure. So this sequence a sub n equals 4 minus 1 over n. So one thing that you can do is we can talk about what happens as n increases. So as n increases, what happens to a sub n? Well, if we let n equal to some number k, which is just going to be a positive integer, then a sub k will be 4 minus 1 over k. And if I were to plug in k plus 1 for k, this would be 4 minus 1 over k plus 1. Okay? Now obviously k is less than or equal to k plus 1. And if you have a larger denominator, that means the fraction itself is smaller. So 1 over k plus 1 is less than or equal to 1 over k. If I multiply both sides by a negative, I have to change the sign. And then if I add 4 to each of those, I get that 4 minus 1 over k plus 1 is greater than or equal to 4 minus 1 over k. So that means a sub k plus 1 is greater than or equal to a sub k for all positive integers k. Okay, so what that tells me then is that a sub k, or a sub n I guess we called it, is monotonic. So the other question is a sub k bounded? So to determine this, I'm going to look at some terms in the sequence. So if I list out the first couple of terms, I would have 4 minus 1 over 1, 4 minus 1 half, 4 minus 1/3, 4 minus 1/4, so on and so forth. And you can see that the amount that's being subtracted off is getting smaller and smaller and smaller. So this thing is approaching 4. It's never going to reach 4, but it is approaching 4. And on the flip side of that, because the number that you're subtracting is getting smaller and smaller and smaller, that number is never going to go below 1. So that tells me that 4 minus 1 over n has to be less than 4 and greater than or equal to 3. So we can say that this is bounded. So since it's monotonic and it's bounded, that means that a sub n converges. And this is a similar example. We've got a sub n equals 2/3 to the nth power. So if you wanted to list out some terms, you would see that you would get a sub 1 equals 2/3 to the first power. A sub 2 is going to be 4/9. A sub 3 is going to be 8 over 27 because I'm cubing everything. And this is about 0.67. This is about 0.44. This is about 0.30, so on and so forth. And what you will find is that this number is going to get smaller and smaller and smaller and smaller. So a sub n plus 1 is always going to be less than or equal to a sub n. It is monotonic. And since it's getting smaller and smaller and smaller and smaller, it's also never going to be negative because you're raising a positive number to a power. So a sub n is never going to be smaller than 2/3. It's never going to be bigger than 0. In fact, it's not even going to be 0. So we say that this thing is bounded and therefore converges. Now, one thing that is important, it doesn't tell us in this theorem, it doesn't tell us what it converges to. It just says that it does converge. And sometimes that can be enough information. It just depends on what you're trying to accomplish with this idea.